The problem is that even though in the root 2 case it's relatively easy to specify those sets because the condition is really just whether a rational number is square is bigger than 2 or less than 2 or negative largely. But if you have a general real number, then getting hold of that Dedekind cut itself is a process that requires an infinite amount of work. In other words, if Dedekind wanted to create his coloring for, say, pi, he would have to first get a sequence of nested intervals that surround pi and that sort of converge towards it, and use that sequence to successively paint more and more infinite quantities of rational numbers. So the Dedekind cut approach appears to put real numbers on a kind of a set theoretical foundation, because now real numbers are sets or pairs of sets of rational numbers. But ultimately, effectively, it doesn't actually escape the problem of having to involve or invoke an infinite process in order to actually create it.
Right.
So in some sense, it's a bit of a linguistic sleight of hand that allows you to make the theory of real numbers seemingly dependent on a prior theory of infinite sets.
Okay.
And that's actually the reason, that's really the core reason why the infinite set story is so important in mathematics, to justify Dedekind's creation of real numbers using this particular system of ideas that he had.
There are some, let's say, counterintuitive conclusions that emerge from thinking of infinite sets. You get, let's put counterintuitive in quotes. For anybody that's not familiar, one of the claims, and again, correct me if I'm wrong, is that we could conceptually have let's say, the set of all positive even integers, 2, 4, 6, 8, 10, and so on. And we can say all of them. So we take every single one and we put them into a set. We somehow put a boundary and say we're talking about all of them. So if you do that, if you play by this line of reasoning, you say, okay, how many elements are in that set? Well, there's an infinite amount of elements. But then you say, okay, now imagine a set of all the positive, even, and odd integers. You have 1, 2, 3, 4, 5, and so on, which seems like there would be more elements in that set. Intuitively, you think, of course, there are new numbers in this set that there weren't in that set. And yet the conclusion is they actually contain the same amount of elements. Is that correct?
Well, I think a mathematician wouldn't say it that way, because we don't want to talk about the number of elements when we're talking about so-called infinite sets.
Right.
But you have to understand, I don't really believe in infinite sets, so I have to take on the position of the majority here in defending it. So they would say, okay, we're not allowed to talk about the number of elements in an infinite set, but what we can do is we can talk about making a correspondence between the number of elements in this set and the number of elements in this set. So if you can kind of match them up, one boy for every girl, then that's some kind of reasonable replacement of the idea that they have the same number of elements. Mm-hmm. We may not be able to count them, but we can see that we can match them up. Mm-hmm. Okay, so that's the way a modern mathematician would want to rephrase that argument.
Okay. Now, is that kind of a euphemistic way of rephrasing it, or is that an incorrect way of thinking of what an infinite set would imply? Is that that, for example, the concept of cardinality is really talking about the number of the distinct elements in the set. So is it a mistake to think of cardinality in the same way that we think of it applied to finite things when you apply them to infinite things?
I wouldn't say it's a mistake, but I think you have to be very careful. And it's easy to distort things by using that language of finite things and the intuition that one has for finite things and trying to apply them to the so-called infinite situation. I think it was Hermann Weyl, or maybe it was Poincaré, but maybe it was Hermann Weyl, who said something about, in the lines of that this is one of the weaknesses of the modern approach with set theory, is that we try to invoke the same arguments for the infinite case as we do for the finite case, but the laws of logic are really different. But look, from my point of view is actually much more simple-minded in the sense that, I believe in writing things down. I have a very computational point of view, and not a very philosophical point of view, in fact. So maybe, I'm a little bit naive from a philosophical point of view. But so for me, a mathematical object is specified when you write it down. And that's really necessary. So one can have fancy thoughts and so on, that's great, but ultimately if I want to convey an object or the idea of an object to you, I'm obligated to write it down. And that's really the problem with thinking about infinite sets, is that we can say things like the set 1, 2, 3, 4, and so on, but you can't actually express that set.
Okay.
In fact, that problem emerges long before we get to infinite sets. It even starts appearing when we get to very large sets. Maybe this isn't appreciated as much as it could be, but that the difficulties with sets theory are not just at the infinite level, they're also at the very big level. Once we get to the idea of numbers that are so big that we need some kind of towers of exponential kind of notation to get at them, then we're already in a realm where a lot of our arguments break down. In other words, there are limits to computation. There are limits to what computers can do, and not because our technology is necessarily limited, or because we're not smart enough yet, or we haven't built enough big enough machine. It's just because the universe is organized in such a way that there seems to be some smallest limit to how much you can compress things, to how you can subdivide space. Like there's a Planck scale sort of limit to how small you can progress, and there seems to be some large scale limit to how big the universe is. So if you put those two together, it means that there's really only a finite number of possibilities that are inherent in the world in which we live. And you can quantify that, at least by if you make some estimates that the physicists can give you. And you can quantify and see that once you reach numbers that are of the order of 10 to the 10 to the 10 to the 10 to the 10, something like that, then you're talking about numbers which now no longer can represent real collections in our world, no matter how small you created them.
Now you say that's not a philosophic position, but that is very much a philosophic position. You're saying that numbers don't exist really outside of our conception of them or outside of us writing them down. Is that fair to say?
Let's say that that's my position.
Okay.
So my position is I'm kind of down-to-earth person. I want to see things written down. To me, that's the litmus test of whether something is real or not. You may have all kinds of ideas, but until you can express them in some kind of way that we can all look at them and compare notes and I can really study them, then to me it's at some kind of abstract level.
Would you say this, and this is also my position as well, would you say that if it's true that numbers don't exist separate of their being conceived, and neither do mathematical formulas, then that necessarily entails a kind of logical finitism, that you can't get to infinity if all the objects you're talking about must be objects of your conception, because you can't conceive of infinity?
See, I guess I would rather not even discuss existence. See, to me, that's a philosophical question, the question of whether, ghosts exist or angels exist and so on. I don't know. It's a philosophical question. I'm a mathematician, and I'm very concrete and down to earth. So the question for me is, what can we write down? What can we compute? What formulas can we come up with that we can take the left-hand side and we can take the right-hand side and we can verify that the left-hand side equals the right-hand side?
So you're agnostic for the other stuff?
Yeah, I'm agnostic. I'm uncertain as to what the word exist really means. To me, the relevant thing is what can one write down.
Right.
Yeah.
Okay. So for anybody that's not familiar with some of the claims about infinite sets and infinity, I think it's helpful. I remember watching a video of yours where you gave an example to the audience about some of the counterintuitive conclusions about whether or not you can actually complete an infinite process, or I believe the example you gave was something like, there are an infinite number of balls over here, and you take a ball and you put it here, if you know what I'm talking about. So if there are some what are some examples of where you get profoundly counterintuitive conclusions when you try to actually complete an infinity?
There are quite a lot of them in modern mathematics. There's quite a lot of unintuitive results that people believe are true, and they're really dependent on prior sort of belief system with respect to real numbers and infinite sets. One could mention the Banach-Tarski paradox, which you're probably familiar with. It's a well-known sort of chestnut that you can take a ball of this size and rearrange it into a finite number of pieces, maybe 5 or 6, and then rearrange those same pieces, move them around, and rearrange them to get a solid ball exactly twice the size, let's say. There's things like non-measurable sets, non-measurable functions, which in modern mathematics are somewhat unintuitive, counterintuitive. There are things like space-filling curves that ostensibly go through every point in a square in the plane. But I think those are all, in some sense, sort of peripheral and ultimately really rather unimportant, because they're results with no consequences. They're sort of gee whiz, isn't that interesting things, but they're completely devoid of consequences because the mathematics behind them invokes these things that you actually cannot do computationally. That's sort of hidden behind the scenes. I think a much better and more interesting example is a belief that most mathematicians have that I think most lay people would find rather astounding. And this actually is a belief that actually has a lot of core implications. So if we look at the interval from 0 to 1, okay, and we think about the numbers in there as infinite decimals. So we may have to convert from a Dedekind cut or a Cauchy sequence point of view to infinite decimals, but they're largely equivalent. So if we imagine infinite decimals between 0 and 1 for a second, then there's this really fundamental dichotomy that was pointed out strongly by Wittgenstein, who you will know is sort of one of the leading philosophers of the 20th century, if not the leading philosopher, most influential. And he said, look, there's really a fundamental distinction between two kinds of infinite decimals. At the one kind, you can think about an algorithmically defined infinite decimal, one that's generated by a computer program, or maybe a function or some kind of algorithm. And on the other hand, there are, or at least one is potentially able to think about, sequences which are not generated by a finite process, for which you might imagine some kind of oracle, maybe in another universe that has an infinite brain and an infinite time. And this oracle just spews out digits for this infinite decimal, but without any prior finite algorithm or pattern.
Okay.
So on the one hand, we have these sort of algorithmic decimals, and the other hand, we have the sort of infinite choice decimals, you might say. Okay. Now, if you actually look in the real world, when you make an integral, or when you compute an arc length of a curve, or you have some infinite sum, or you do one of the many things that mathematicians actually do involving some infinite process. If you do believe and you allow them to get some result, you will always, or almost always, get one of these first kind of infinite decimals. They're necessarily algorithmic decimals. But the belief system that modern mathematicians almost universally share is that most of the numbers in the interval 0, 1 are actually not of the algorithmic kind. They are of this infinite choice kind. Which means that in fact, the numbers that we use actually in practice are a minuscule fraction. In fact, measure zero is a terminology that's used. So a measure zero subset of all of the real numbers. So this is some kind of fantastical belief system, really, that most of the numbers that are actually there are ones that are completely inaccessible to us and our machines.